Hello everyone. As I understand, we are ready in Budapest to start this session. And this session is about synthesis and context. I'm going to share this session. And the first speaker here is Pilar Opuzil Gallegos, talking about comparing acoustic and textual representation of previous linguistic contexts for improving TTS. Pilar, the floor is yours.
Thank you for the introduction and for saying the title of the paper. Long title. I'm going to check the audio.
The rentals of rooms and fees went to the ward.
That's working. Yes,
okay,
thanks.
Perfect. Thank you. Okay. So, all right. Well, thank you for attending this presentation. Like Thomas said, our work is on comparing acoustic and textual representations of previous linguistic contexts for improving text-to-speech. Generally, when we train our TTS models, we train them with utterances that we assume they are independent from each other, even if they actually come from a larger unit like a paragraph. So even if originally they are inserted in a linguistic context where they are related with other utterances, that information is lost during training. So recently there has been a few works that propose to exploit the use of linguistic context to improve TTS by conditioning the model into that context. So to be very clear, when we talk about context in this presentation and in the paper, we mean the previous sentence. I know context can mean many things. So just to make it very, very clear, for example, let's say we have these 3 utterances from the LJ dataset, then our target utterance is the one we're training with or the one we want to synthesize, and the context is the immediate previous utterance in this example. And we want to learn this relationship. That's what we want to learn when training. So like I said before, there has already been a few works where they use this information. For example, in this paper from Amazon, they use linguistic and acoustic distance from previous utterances for multi-sentence synthesis when using a VAE for inference. In these 2 papers, Tacotron 2 is conditioned to previous and also next utterance BERT embeddings by concatenation to condition the model. And in our previous work, we conditioned the model on previous utterance acoustics, a representation derived through GST tokens that also, a method that also included an additional loss. So our research question has to do with the fact that we already have evidence that conditioning can improve TTS, but you saw that all the different works are representing context in different ways. So we wanted to study how should we represent that context. And specifically, we wanted to analyze 3 different variables. We wanted to compare the use of acoustic or textual features from the context, compare the use of representations extracted from large pre-trained models versus training encoders jointly with the TTS to extract such representations. And finally, if these representations should be at the utterance level or at the word level. Our base architecture is FastPitch, an architecture developed by NVIDIA that is a transformer-based TTS with explicit duration and explicit pitch prediction. And we basically do this. We include our context methods with our different combinations, and we sum them here to the encoder inputs, which is a combination of the embedding of the phonemes and of the positional embedding of the target sentence. And again, the context representation corresponds to the previous sentence. So our experimental design looks to combine all these different variables on how do we represent context. So we have different paths we can take. This is like a template of our experimental design where we have this context utterance and we can extract either acoustic or textual features then both of them can either go to a pre-trained model or be used jointly with an encoder that is jointly learned with the TTS. And then from either of these, we can either extract word level representations or utterance level representations. And depending on these, we need to either obtain a vector that has the same length of the phoneme so that we can sum it in the model as I showed previously here, or that is just one vector so that with a hidden dimension so that again, we can sum it. So I'm gonna go through the 8 different conditions we had by combining this part of the experimental design. And then I'm gonna go into the detail of what are these 2 methods. So first we have the conditions of acoustic features with jointly learned encoders. In the first case, we extract MEL spectrograms from the context utterance. We use a context encoder that extracts just one vector for the whole utterance. It's a global encoding of the context. And in the second case, instead of a context encoder, we have a convolutional block that will give us a representation in time. And that representation will be averaged at the word level by using word boundaries. And in that way, we obtain a word level representation. Then we have, again, acoustic features, but now using large pre-trained models. And in this case, we use a deep spectrum model. This is a method that uses spectrogram plots as input and leverages a large pre-trained image classification network from which we can obtain an embedding. So if we use the plot of the whole utterance, we can obtain a global vector. This is our utterance level method. And if we take plots of fragments or windows of that utterance, we can obtain a representation across time. In this case, we use the fixed window just to simplify things of 1 second. So it's not actually words, but it's something like that. It's in any case sub-level from the utterance. And then we have the textual features with jointly learned encoder. In the first 2 conditions, we use the phonetic transcription of the previous utterance. And you can see that here we have the same configuration as we had before, where we have either a context encoder to obtain one global vector or a convolutional block for which the output is averaged at the word level to obtain a word level vector. And finally, we have textual features with a pre-trained model for which we obviously use BERT, where we have the text tokens of the previous utterance and we either average them to obtain a global vector, or we have at the word level, one vector per token. So now I'm going to describe in detail these 2 boxes that, as you can see, they repeat for all the utterance level conditions, and for all the word level conditions, they are the same method. So first, for the utterance level method, like I said before, we obtain this utterance level representation that I showed before. And we can actually simply use this representation, but we saw that if we add a global style token layer, the results improved. So we use this as input for the GST, and this process context is the one that is actually summed here for the utterance level condition. And then for the word level context method, which is a bit longer to explain, but it's actually very simple. The goal is to actually select the words in the context that are relevant. So how do we do this? We already have the word level context representations that I showed before, and we also have the words in our target sentence. And what we do is that in the first step, we use an attention method to calculate the relationship between the 2 sets of words. So let's look at an example. If in the word utterance, if in the context utterance, we have 25 words, and in the target utterance, we have 7 words, then this attention will give us a vector of the maximum weights with a length of 7. So what this means is that the fourth word in the context is the most relevant for the 0th word in the target sentence. And we can actually inspect the results of this process. So for example, here we have a real example where you have the context words and the target words. And these are the maximum weights that you obtain for it. So once we have this analysis done, what we do is that we collect the word level vectors that are the relevant ones given the weights. We concatenate them. So now we have a vector of the same length of the target sentence words. And then we simply upsample it using the word durations to match the final dimension of the phoneme so that we can again add it at the sum here. The specific implementation of how we do both methods is not really as important as to simply have a way of comparing the difference between global and word level. So we use the LJ dataset. In terms of preprocessing, we use MFA to align the data. Like I said before, we use FastSpeech as the base architecture, and we use Wavelet as a vocoder. And for feature processing, we have Deep Spectrum BERT and the global style tokens. So we have a lot of conditions to test. We have 8 different combinations for the models using context, and we have our baseline. So we actually divide the evaluation in 3 different parts. First, we compare all the acoustic context. Then in a second part, we compare all the textual context. And in a final evaluation, we compare the best systems. So the results for the acoustic context is that the one using deep spectrum at the utterance level is the only one that is significantly different to the baseline. And for the textual context, all of them were significantly better than the baseline. So for the final evaluation, we compare the baseline with the best acoustic model, deep spectrum utterance. We selected the best one of the textual context in terms of significant results, which was the text word with the phonetic transcriptions. And we add 2 new models, which are combinations of the acoustic and the textual context, so that we can see if by using both, we obtain better results. So in the final test, the best model was the one combining deep spectrum at the utterance level and BERT tokens at the word level from the context, both at the same time. This was significantly better than the baseline. So let's listen to some samples. The sample is very short just because of the time, but I hope you can get an idea of the results. So this is the ground truth.
His letter to the corporation under date 4th June.
Baseline.
His letter to the corporation under date 4th June.
And the context methods.
His letter to the corporation under date 4th June. His letter to the corporation under date 4th June. His letter to the corporation under date 4th June. His letter to the corporation under date 4th June.
So naturally what everyone will be wondering now is what is the context actually doing, or how it's affecting the system. So we will show a very, very brief qualitative analysis to try to give some intuitions on this. And what we do is that we synthesize the same target sentence, but we choose 3 different contexts randomly to synthesize that sentence so that we can see what are the differences. So if we have this model that is using only the acoustic context at the utterance level, we can see that we have differences in pitch and in speech rate, and these are global shifts. If we have BERT at the word level, we can see that there are changes in emphasis in the different renditions of the same sentence. And when you have the model that uses both techniques, these effects are combined and others disappear. For example, the speech rate doesn't change anymore, but you have the lower pitch and you have the differences in emphasis. Don't have time to play the samples, but we can play them later if you want. So in conclusion, we show more evidence that context can improve TTS, and this mainly affects the prosody of the systems. In terms of our specific research questions, we see that combining text and acoustics from the context yield the best results, that pre-trained models outperformed training jointly with the TTS, these representations, and acoustic features seem to be better suited for utterance level representations, while textual features for word level representations, which it makes sense in a way. And finally, in terms of limitations, we didn't evaluate these models in context. And we didn't do it because there's still a lot to be done in terms of the design of these evaluations. And we're working on that in parallel. You might have seen yesterday, Joanna's presentation was about this. So it's something we are looking at the same time. And in terms of future work, there is a lot to do. There is a lot to understand. The method that we represented here is not particularly interpretable, but we will try to see if there is a systematic interaction between context and targets. Also, some papers are already applying these methods for dialogue data to see if they can model entrainment between speakers. This is a paper that I think will be presented at Interspeech next week. And finally, we are also seeing, analyzing how the proficiency of the speaker and the level of how spontaneous the data is matters a lot in how big is the effect that you get by using these methods to improve the TTS. So here are the references, and that's it. Thank you.
Thanks a lot, Pilar. I think we have time to go back to your slide 31 to play some samples.
Sure. So, so yeah, remember this is the same sentence, but driven by 3 different contexts. So it's the first one.
The rentals of rooms and fees went to the warden, whose income was £2,372. The rentals of rooms and fees went to the warden, whose income was £2,372. The rentals of rooms and fees went to the warden, whose income was £2,372.
That's, I think they were in the same order, blue, orange, and green. Yes.
Thanks, Pilar. Time for questions. Any question in the chat? I don't see anything yet. Any question on site?
Hey, yeah, I wonder if you could just discuss a little bit, compare with this P&G BERT paper, maybe, that uses phonemes as inputs as well as text. If you've seen that.
Yes. Yeah. Well, I don't. Thought about that. Yeah, I don't think there's a direct relationship. I think what they were doing is trying to mix the representations of phonemes and characters to obtain embeddings. But that would certainly could be used as a feature to represent the context. And if we haven't tried, it's simply because we don't have a lot of data and resources to train our own BERT for our own phoneme symbols, but it could be something that we could apply. Hello.
Hello, I have a question. For when you are biasing, in fact, the system with text, there is no discrepancy between the training and the test because you have just text. But if you are biasing with the acoustics,
yes.
In fact, the previous utterances when you are training, it's ground truth. But for test, it will be the utterance you have synthesized with context, which were synthesized with the preceding context, which
yes,
blah. So
yes.
Do you take this into account in your evaluation?
Well, for the evaluations that we show in the paper, we're using the ground truth to synthesize it. But in the web page with the samples, you can listen to utterances using the synthesized context.
With listening, but for the evaluation, so the
Well, my point is that there is not a lot of difference. It's not like the system drops in quality or anything like that. So yeah, we've tested it, and we've actually also tested it synthesizing a whole paragraph. So you could think that maybe the quality would sort of like drop gradually, but it doesn't, because you also have the text, so you're kind of anchoring a bit on the text, and the quality of the model is not bad, so you don't really have this domino effect. It keeps working pretty well. Yes. And also, sorry, you could have a less detailed acoustic representation. We've also tried to use delexicalized speech as input for the context. So you only have like a prosodic representation instead of the whole detail of the MEL spectrograms. And that also works, yeah.
And so do you think about a resetting mechanism, for example, when you jump from paragraph to paragraph, so that to somehow break this dependency?
You could do it. So for the very first sentence, we have like a special context, which is like silence or like a start token, right? So if you wanted to reset, you could use that one, yes.
Okay, thank you.
Thanks, Joel. We have two questions also from the chat. Question from Alexandra Torres Quintero. Can you give us an example of a context that you used?
Well, the contexts are which I used where. So like I show in the very first part, the contexts are the immediate previous utterances. So that is just defined by the data set, right? So in this case, we have LJ, we have utterance 1, 2, 3. If your target sentence is 3, then the context is utterance 2, and so on.
Right. Thanks. And last question from Rob Clark. Do you have a notion to what you gain from the acoustics if the utterance level is better? Is it just variation between sentences, sentence, or something else?
We are working on analyzing what is the interaction that is happening. But I think that it's mostly a thing of coherence. So like that the model doesn't jump to a whole different speech rate or speech range, but you have a bit more of a continuity between the samples. And in this specific paper, we didn't drive the context representation with any loss, but we've seen that you can add extra losses to force the context to exactly do that if you want to do that. So I think the context could actually be used for different things if you can actually design a loss that can force that context to do what you want to do.
Right. Thanks again, Pilar. Very interesting. We need to move to the next talk. Thanks again. Next speaker is Wataru Nakata. Wataru?
Yes, can you hear me?
Yes, I can hear you.
Let me share my screen. Okay.
And we can see. Go ahead.
Thank you. Hello, my name is Wataru Nakata from the University of Tokyo. Today, I'll be presenting audiobook speech synthesis conditioned by cross-sentence context-aware word embeddings. First, let me explain what audiobook speech synthesis is. So in conventional audiobook creation, the speech is done by professional speakers. And since the duration of speech can be very long, it leads to increased cost and time. For example, the first book of Harry Potter is approximately 8 hours long. This is one of the reasons why the audiobook available titles are limited. On the other hand, in audiobook speech synthesis, which aims to ease the burden to create audiobooks, the speech is done by speech synthesis models, and this significantly reduces burden to create audiobooks, and more books will be available in audiobook. And it is also have been studied as emotional TTS, such as GST Tacotron, TPGSD, or result challenges where the audiobook was used as a corpus. So next I'll talk about the challenges in audiobook speech synthesis. The first challenge is to achieve prosody reflecting neighboring context, which is our contribution. For example, consider the passage here. She whispered in my ear, you won't believe it. When professional speaker read aloud this passage, the first sentence, the whispered, affects the following sentence, you won't believe it. The second challenge is achieving character acting at dialogues. In audiobook speech, the speaker often changes their voice style depending on which character is speaking. For the speech synthesis model to do this, the model has to consider the character's gender or age or the personality, but these attributes are hard to infer from text. In this work, we address the first challenge using cross-sentence context-aware word embeddings from BERT. So the research outline is as follows. Our purpose is to achieve synthetic speech prosody reflecting neighboring context for audiobook speech synthesis. To do this, we have conditioned speech synthesis model by cross-sentence context-aware word embeddings from BERT. In experiment, we evaluated synthetic speech on 1 and 5 consecutive speech to assess quality as audiobook speech. And the result shows that the use of cross-sentence context-aware word embeddings improved the synthetic speech quality as audiobook speech. Next, I'll talk about cross-sentence context-aware word embeddings from BERT. So the BERT is a de facto standard method to extract embeddings from sequence of words. And the recent works show that these embeddings are also useful for sentence-wise speech synthesis. It is also used to extract cross-sentence context-aware word embeddings by inputting multiple sentences. In this work, we focused on the characteristics of BERT that it can capture cross-sentence context. And we conditioned speech synthesis model by cross-sentence context-aware word embeddings from BERT. So next, I'll talk about the outline of proposed model. So the proposed model is based on Tacotron 2, and the Tacotron 2 is conditioned by the linguistic information from BERT. As you can see on the right, the Tacotron 2 encoder output, linguistic features from BERT is concatenated to the Tacotron 2 encoder output. To show the effect of using cross-sentence context, we evaluated 3 models, the Tacotron 2 on single sentence on multi-sentences. First, I'll talk about single sentence. The single sentence, on the right-hand side, you can see the architecture of single sentence. Single sentence gets only the current sentence to be synthesized as input and outputs corresponding meta spectrogram. On this example, the input sentence goes through a Tacotron 2 encoder and BERT. And then the BERT output goes through a CW encoder and then concatenated to the Tacotron 2 encoder output. When concatenate, since the Tacotron 2 encoder output is word wrong and the CW encoder output is, the Tacotron 2 encoder output is character wrong, while the BERT output is word wrong, we simply duplicated each embeddings by their character counts. This model does use CWE, which is context-aware word embeddings, but it does not use cross-sentence CWE. Next, I'll talk about the architecture of multi-sentences. Single sentence and multi-sentences are similar, but multi-sentence inputs not only the current sentence to be synthesized, but also its neighboring sentences. Therefore, this model uses cross-sentence CWE. And in this work, we use two previous sentences and the current sentence to be synthesized as input. Okay. Next, I'll talk about the pros and cons of fine-tuning BERT. In this work, we have also evaluated the effect of fine-tuning BERT in audiobook speech synthesis. The pros of fine-tuning BERT is as follows. The first pro is the potential performance gain. And in fact, the recent work reports that fine-tuning of BERT was pivotal. And the second pro is that the BERT's output gets optimized for audiobook speech synthesis. On the other hand, the training can be very unstable. In fact, the catastrophic forgetting was very common to occur in our cases. It is also very computationally very expensive. Therefore, we have also evaluated the effect of fine-tuning BERT in audiobook speech synthesis. Finally, we prepared 5 models for evaluation. The first model is Tacotron 2 and single sentence without performing fine-tuning on BERT, and multi-sentences without fine-tuning on BERT, and single sentence fine-tuned, which performed the fine-tuning on BERT, and multi-sentences fine-tuned, which performed the fine-tuning on BERT. Experimental conditions are as follows. For dataset, we used JSUT and JCAC. And this is because we couldn't be able to converge with only using JCAC. The model is first trained on JSUT, which is composed of isolated sentences. And then after the training, the model is trained on JCAC, which is a Japanese audiobook speech by single male speaker. For multi-sentences neighboring sentences, we used current sentence to be synthesized and the 2 previous sentences. For objective evaluation metrics, we use average Merrill-Capstrau distortion and gross pitch error. For subjective evaluation metrics, we used 1-sentence samples and 5-sentence sample. For 1-sentence sample, we performed naturalness MOS test, and on 5-sentence sample, we performed naturalness MOS and A/B test as audiobook speech to assess the quality as audiobook. Okay, so next I'll talk about the results. On the left-hand side, you can see the result for the Merrill-Capstrau distortion. And on the right is the gross pitch error. For MCD, the difference was marginal in all compared models. On the other hand, on GPE improved on the model with cross-sentence CWE. And this result shows that the synthetic speech gets closer to human speech by using cross-sentence CWE. Next, you can see the results for naturalness moss. On the left is a naturalness moss on 1 sentence sample. And on the right is a naturalness moss on 5 sentence sample. As for the 1 sentence sample here, the naturalness decreased compared to Tacotron 2 in all models. However, on 5 sentence samples, multi-sentence fine-tune was significantly better than other models. And this result shows that while the synthetic speech is less natural in isolated sentences, on 5 sentence sample, the use of cross-sentence GWE helps to improve naturalness. Also, we saw the improvement by performing fine-tuning of BERT. To further assess the suitability of synthetic speech as audiobook, we conducted A/B tests in which raters are asked which 5 sentence sample is more preferable for reading of a picture book. As you can see, the multi-sentences, which is shown in bold text, is more preferred as reading of a picture book. Next, let me play some speech samples. And the color for each sentence shows the style, the correct style for each sentences. Blue for the narrative, and red for non-narrative sentences. Yes. In this case, the speech style for narratives. So this blue 3 should be similar. Please listen carefully to the style of the 4th sentence. First, I played single sentence fine-tuned.
クッキーを頬張りながらアリくんが言いました。このクッキーいいしいね。とっておきのケーキもあるのよ。おいしいおやつを前にみんなウキウキルンルンルン。ところが気に入らないのはカエルくんです。
Next, I play multi-sentences fine-tuned.
クッキーを頬張りながらアリくんが言いました。このクッキーおいしいね。とっておきのケーキもあるのよ。おいしいおやつを前にみんなウキウキルンルンル。ところが気に入らないのはカエルくんです。
On multi-sentences, the narrative sentence, which is shown in blue, have similar styles. However, on single sentences, the 4th sentence style was more similar to the non-narrative sentences. These kind of errors were very common in single sentence, as it cannot see the neighboring context. On the other hand, the multi-sentence achieves correct speaking style on most cases, and more samples are available on this page. In summary, our purpose was to achieve synthetic speech prosody reflecting neighboring context for audiobook speech synthesis. To achieve this, we conditioned speech synthesis model by cross-sentence context-aware word embeddings from BERT. And the result shows that use of cross-sentence GWE improves synthetic speech quality as audiobook speech. Also, the fine-tuning of BERT further improved synthetic speech quality. For future work, we evaluate the proposed model with entire paragraph as neighboring context, or use of non-textual information such as paragraph numbers. Lastly, let me talk about the corpus by the 3rd author. The Japanese Kamishibai and audiobook corpus, JCAC, which is used in this paper, is publicly available. It contains 48 kilohertz sampled audio of 42 audiobooks. We did not use in our experiments, but the corpus also contains the illustration of book. Furthermore, the third author released yet another corpus called JMAC. This corpus contains speeches by 39 professional speakers with in total of 32 hours. Check them out to enhance their research on audiobook speech synthesis. Thank you.
Thanks a lot, Wataru. We have room for questions. I don't see anything in the chat. In the meantime, I'm not super familiar with Japanese BERT. Can you explain me how comparable it is to the, to the English version?
So the tokenization process can be a bit different since the Japanese doesn't have white spaces. So the tokenization can be different on which software you use. So yeah, it is more complex.
And it's trained on what kind of data? Do you know?
The BERT we use in the experiment. Yeah, the model is the BERT is trained on Japanese Wikipedia and the Japanese copyright outdated novels. So the domain should be similar.
Right. Okay, thanks a lot for clarifying that. We have time for questions. Anyone on site? I have one question before going to you on site, if you're fine. In single sentence.
I have one question.
Go ahead.
About how you generate the audiobook, because we had similar experiments a few years ago for Hungarian, and it turned out that we were not able to automatically extract the particular character of the audiobook from the text. So in order to not to have just a monotonous single voice, but to have like a general announcer and then various voices for the various characters, it only worked if we manually input some voice character for a given text. And actually for an experiment it worked, but otherwise for a longer term thing it was not viable. The question that could you solve this problem so that automatically identify from the text who is speaking and then switch the synthesizer voice accordingly?
Okay, so thank you for the question. I think maybe this is only for Japanese, but we could see the difference between the male speaker or female speaker, as they have a different kind of different use of Japanese. So we could differentiate, the model could differentiate the female character is speaking or male character is speaking, but we couldn't go farther than that.
More than one female or more than one male?
I'm sorry?
What happens if you have not just two characters, but you have maybe 5, 10, whatever. For example, in a novel, you have various people, slaves, lords, waiters, I don't know, cooks, and so on.
Yeah, so we could, so the model seems to see the gender of the character, but since the model cannot guess the age or other attributes of character, the speech was more like was not like fitting the character personality or something like that.
Right. Okay, thanks. I see a question from the chat. The question is, in single sentence, does BERT use a single sentence and a single sentence is synthesized, or does BERT receive context but single sentence is synthesized?
Okay, thank you for the question. The answer is that the single sentence does only use the single sentence. So it doesn't see the neighboring sentences.
Right.
Yeah, so it doesn't use context. Yeah.
Got it. I had one more question on your side. When you had one sentence scenario and the 5-sentence one, right? In the one sentence, you had quite severe degradation compared to the Tacotron 2 baseline, right? How do you explain that?
I think it was because the expression was didn't make sense in isolated sentences. So in audiobooks, some samples contain a screams, or some weird sound, which does not make sense in isolated sentences. And when you perform evaluation on one sentence samples, that of course the listener cannot differentiate, cannot maybe get confused by the listeners cannot see the context, the neighboring context. So those expression might contribute to the lower mass.
Okay, I see. Thanks a lot, Wataru. We have only 1 minute, so one very short question, or we move to the next speaker. Nothing in the chat, so let me thank you again, and we move to the next talk. Thanks. Presented by Manoranjit.
Hello, am I audible? I'll just, yeah, just a second. Am I visible?
Yes, I can hear you and I can see you.
Yeah, so let me go ahead and share my screen. I think my screen is visible.
I can see that, yes.
Yeah, it's okay. Okay. So let me start. Good afternoon, everyone. So I'm Manoranjit. I'm here to present my work, lip syncing efforts for transcreating lecture videos in Indian languages. So let's get just a second. Let's get started. So this will be the outline of the talk. So first, I'll be talking about. I will introduce ourselves to video transcreation system, and then I will talk about the motivation behind the work, and then let's see about the preliminary systems that we have attempted in this work, and then I'll briefly discuss about the proposed systems discussed in the work, along with the evaluation setup and their results. So first, what is a transcreation system? So basically, transcreation is a concept that is borrowed from field of translation, which basically means to convey a message from one language to another. So here we are trying to transcreate lecture videos. So we have a source video. We extract the audio from the source video, and then we do an ASR on the audio, and we get an SRT. So basically, the SRT will have timestamps along with the transcriptions, and then we do a manual correction on this SRT, and then we translate the SRT and synthesize the SRT, and then we again manually correct it and synthesize the SRT in the target Indian language. So after synthesizing, we have the TDS synthesized output along with the timestamps, along with the video, which is given to the lip syncing module to get the lip synced video. So in this work, we are going to briefly discuss about various techniques that we have attempted for lip syncing. So the motivation behind the work has always been to make the educational content that is available in internet to as many people as possible. So now that India uses more internet users, and 58% of them access it for online education, And also not only that, India is also home to several languages. It also has several medium of education. So transcreating these lectures into Indian languages will make it more useful. Now that COVID has hit us, we have looked into online education more than ever. So before getting into the work, let me just give you a simple overview about differences between lip syncing and dubbing. So basically, dubbing is a process in which sound is recorded such that it matches the already shot motion picture. So in dubbing, the text is carefully translated such that it matches the duration of the source, and that audio is also recorded under studio environment with trained and professional artists. Usually dubbing is an labor-intensive and expensive task, whereas lip syncing is a process in which the lip movements are made synchronous with the audio. Unlike dubbing, we don't put much attention into the translated text. So in this work, we are going to see about isochronous lip syncing, which is basically we are trying to match the speaker's lip movement with the audio. So let's get started. So before going into this, these were the challenges that we faced during that we faced during transcreating the lecture videos. The important thing was the lecture videos are often impromptu speech or unpracticed speech. So the lecturer usually is disfluent and makes long silences. The lecturer will also make silences when he is making use of a board or a presentation. On top of this, the Indian language audio is particularly longer or shorter than the English audio. So this also adds as a challenge. So as our initial attempt to video transcreation, we used a Google API-based open source transcreation system. I'll just play the video and then let me talk about it.
ये आज होने जा रहा है रूपरेखा हम सिर्फ याद करेंगे क्यों कर फाइबर ऑप्टिक सभी संचार प्रणालियों के लिए रीढ़ है उस तरह की पुनरावृत्ति करना आपकी जरूरत है किसी भी संचार प्रणाली के लिए रीढ़ की हड्डी के रूप में ऑप्टिकल फाइबर तब हम इस बारे में चर्चा नहीं करते थे कि हम पाठ्यक्रम में क्या कर रहे हैं ताकि आज हम करेंगे टुडे तथा पाठ्यक्रम के अंत में आप क्या कर पाएंगे to do.
So as you see, more towards the end of the video, the audio became very faster. So the reason for this is in this particular system that they have used, they have resampled the audio instead of video. And not only that, they've also retained the original English audio in places of the silences or pauses. So whenever the lecturer grasps something, they have put back the English audio as it is back in the video. So this was unpleasant to the viewer. So we decided to work with resampling the video instead of audio in our attempts. So this is the first preliminary system one that we designed for creating a lip syncing video, where basically we have the source video, and then we extract the audio from it, and then we segment the video using the SRT file that we obtained from the ASR. And then we just do a simple resampling of the SRT segment and then create a lip sync video. So this system also had some drawbacks. Before discussing into the drawbacks, let me just play you the video so that you will get an idea of what I'm talking about.
हम उस IT नोड का चयन करते हैं तो उसके संबंधित नोड को वह लेबल मिलेगा जो आप चाहते हैं। तो मूल रूप से हम कह रहे हैं कि इस तरह का यह डिसीजन ट्री बिखरने वाला है अगर मैं इस परिकल्पना के साथ
So basically, if you see in this video, the speaker is speaking very fast and very slow. And he is also speaking in the regions where the video shows that the speaker lips is not moving, but there is this audio. So the reason for this is there are long silences in between an SRT segment, which was not handled. And also the duration difference between the target and the source audio was very large. And while we resample it, the video became faster. So these were the issues that we found in preliminary system one. We wanted to address this in preliminary system two. So in preliminary system two is basically the same system as preliminary system one, except the fact that instead of basic resampling, we do silence detection. So we detected long silence regions in the source audio, and we detected short silence region in the TTS synthesized audio. and then we align it using an algorithm that we developed. And then after aligning, we just resample the video and lip sync the video again. So before getting into preliminary system 2, let me just explain into the algorithm that we developed. So basically, we have two segments, audio segments, a source audio segment and then a TTS audio segment. And we do long silence detection on the source audio, and then we detect silence, after which we find a ratio such that, so suppose find a ratio such that the duration part of the audio before the silence and the part of the audio after the silence. So basically, we split the source audio into two, such that it has two parts, the one before the audio and the one after the audio, after the silence, I mean. So once after we split this, we try to split the TTS audio in the same ratio as close as possible as the source audio. So say suppose if we have split the source audio at 70% and 30%, we try to split the TTS audio and in the ratio as close as to this. Once after splitting, we will recursively call the silence detection algorithm until the split can't be made any further. After getting the map files of audio segments and TTS segments, we just resample the video and lip sync the video. So before discussing about the drawbacks in preliminary system 2, I'll just play a video so that you'll get an idea of what I'm talking about.
I not by root 2 यह कब I not का आधा हो जाता है 60
So if you had looked into this video, the speaker made a pause between root and 2. So the main issue with this preliminary system 2 was it was making pauses in between words that are in between words that are co-articulated together. Not only that, it also detected short silences in between certain words. Since we used the silence detection algorithm, it detected silences in between a word as well. So that showed up here when the audio has been split between root and 2. So to address these, we went into and to address these, as well as we had the textual information from the ASR, we went into the proposed system 1, where we used the word level alignment from an ASR. So here we use HMM-GMM model, which is trained on the synthesized audio and the transcription converted to a common label set format using unified parser for Indian languages. And then we get the word alignment from the HMM-GMM ASR, and then this alignment along with the silence detection, long silence detection for the source video, and we align it using the same algorithm that we discussed previously. After this, we resample the video segment and get the lip sync video again. But the problem with this proposed system 1 was, I mean, it was correct, but it was misaligned by few milliseconds in certain words. So as you can see in this image, this is a spectrogram of an Hindi utterance named Yaha Aaj Ke Ruparekha Hai, which roughly translates to, this is today's outline. As you can see here, the word boundaries are misaligned by few milliseconds. Although this is, might be small, but it shows up in the lip sync video. So these misalignment can be problematic. I mean, will degrade the performance of the lip sync video. To address and let me just give you an example for that.
जो मैं आपको ऑप्टिकल कोरेंट कम्युनिकेशन के लिए विशिष्ट संदर्भ देगा.
So here the speaker paused in between K and Lie, and the boundaries were not proper, and that introduced a noise here. So to address this, we went into a better ASR system, which gave a better boundary. So it is same as the previous ASR system, but here we correct the word boundaries using signal processing cues such as group delay. After correcting, we take only the word boundaries which has a low short-term energy at the particular boundary. So basically, we have the word boundary and we see if the word boundary has a higher short-term energy or a low short-term energy. If it has a higher short-term energy, we just ignore the boundary and then we take the next boundary, so that the lip sync video doesn't have any noises in it. So after that, we send it to the alignment algorithm and we resample it and we lip sync the video. Here is the example for the co-articulated, and this is the short-term energy part that I was talking about. So there are certain words that are co-articulated together. Say suppose in a lecture, the professor says metro network. These are often said together, like in the sense. So here is an image which has an energy plot of the word metro network, and this is the CLS text of metro network, and this is the waveform. So as you can see here, if we split the audio after metro and not metro, you can see that the energy is high. So basically, if we cut the audio here, it will introduce the noise and lip sync video, which will be unpleasant. So basically, what we are doing is we are computing the ST at the particular point, and if it is higher, we are just skipping this boundary and taking the next boundary that has low short-term energy. So here's a demo. I'll play the demo. So this is a source video and this is a target video. I'll first play the source video and then I'll play the target video for the comparison.
So for this, what are the things we know? First thing, we are going to start with, we are going to assign a label to something, right? What is that we are going to assign a label? We are going to assign a label to, let's say, some instance. To be concrete, let's take some example. Let's say you are a stock enthusiast and you want to predict your stock is going to.
So I'll play the target lip sync video.
हम इसके साथ शुरू करने जा रहे हैं. हम किसी चीज को लेबल असाइन करने जा रहे हैं. क्या है कि हम एक लेबल असाइन करने जा रहे हैं. हम कुछ उदाहरण के लिए एक लेबल असाइन करने जा रहे हैं. ठोस होने के लिए आए हम कुछ उदाहरण दें. आप एक स्टॉक उत्साही थे और आप प्रेडिक्शन करना चाहते हैं. आपका स्टॉक जाने वाला.
So this is the demo. So I had showed the spectrogram of IHK Rupareka previously from proposed system 1. So this is basically the same image after the boundary correction based on group delay. As you can see here, the boundaries are much better accurate and precise than the boundaries that are obtained from just the HMM-GMM ASI. So for the evaluation, we had a set of 15 evaluators asked to evaluate 5 lip sync videos, each approximately 1 to 2.5 minutes. And they were asked to compare it along with the source video. We did a mean opinion scores to evaluate the system. And the 5 speakers were chosen, 4 speakers were chosen such that there were 2 male and 2 female speakers. The evaluator were asked to give a rating between 0 to 100, where 0 being no synchronization between the audio and video, and 100 being a perfectly lip sync video. We compared our proposed system along with the baseline system that transcreated transcreates video using a Google Cloud API. So these were the results that we got. The proposed system 1, which used the HMM-GMM ASR assignments, got a score of 75.64, and the proposed system 2, which used the word boundaries and corrected using group delay, got 82.55. And the baseline system that we saw initially got a score of 62.98. The reason why the baseline system that used Google Cloud API got a less score was it resampled the video and basically it became unpleasant to the user. So these are the references, and if there is any questions, I can take. Thank you.
Thanks a lot, Manu. There is one question from Arun Baby. How accurate were the boundaries with group delay correction? Do you apply any manual check?
Just a second, I'm just trying to switch in between the Zoom tab. Sorry, can I get the question again?
Sure. How accurate were the boundaries with the group delay correction, and do you apply any manual check?
The boundaries are pretty much accurate, like in the sense the group delay boundaries are said to be having the group delay boundaries are basically group delay boundaries corrects the boundaries. I mean, the boundaries are accurate as shown in the image. I think I had shared the spectrogram images. So if you had looked into it, the boundaries are precise. So this is already established work that is done before in my lab. I mean, I referred to the paper as well. So basically, that paper shows that the group delay boundaries correct the word boundaries even more precise. So in my lab previously, they have used this group delay based segmentation to correct the word boundary, correct the transcription for better TTS. synthesis, better TTS training. Yeah.
Right. Thank you. More questions? Nothing in the chat. Anyone on site? In the meantime, right, while we may have other questions, what is the target languages that you are targeting?
We are targeting all Indian languages, although the test and results were conducted on Hindi language. Yeah.
But you go for more, right? You go for,
yeah, we go for more. Yeah,
Kannada, Telugu.
Yeah, Kannada, Telugu, and Tamil and everything. We have attempted in every language, but
right.
the results are on Hindi languages.
How challenging is it, right? And your source language is always English, is it, or?
The source language is always English.
All right. I don't know much about Indian languages, right? But how challenging is it in the sense, if I were to, let's say, languages I know would be, for example, from English to German. German is a more convoluted, inherently the sentences are much longer in comparison. So that would be, I guess, pretty much challenging for this kind of task. What is the case for those Indian languages that you're mentioning?
Yeah, so the thing is, the Indian languages are generally said to be longer than the English utterances. So this was one of the challenges. But since we are developing an ASR, I mean, we are getting the SRT segments from the ASR. I mean, we are manually correcting the SRT such that the duration, I mean, such that the sentences are we don't choose a long phrase of sentences and do lip syncing on it. I mean, we choose it such that it is appropriate. Yeah, I mean, between Indian languages, there is no difference, but between English and Indian languages, the duration differs. I mean,
but what do you mean we chose them to, to match? Are you saying for it works only in certain scenarios and not others?
Yeah, so I get your question. So basically, we do ASR on the audio of the video. And then there are certain segments in which the user the speaker just says a word or something. So we make sure that the SRTs are like in the sense evenly timed, like in the sense if one SRT segment is of say 20 seconds or 10 seconds, we make sure that the next SRT segment is also 20 seconds or 10 seconds so that the lip syncing module doesn't suffer. So the thing is, if there is any if the lecturer has said just one word, we merge it with we merge the timestamps with the previous SRT segment so that it becomes equal. So yeah.
Great. Okay. Okay, thanks. Are there more questions? So do you then envision a sort of rephrasing to make sure that the target timings are compatible with the original ones?
During translation, you mean?
Or post-process of the translation, right? Or during translation itself? Mm-hmm.
Yes, we could do that. But in this work, we have not attempted that. I mean, we could post-process the text such that we can match the duration or something. Basically, that becomes dubbing. The main goal of the paper was just to resample, just to use with others.
Got it. More question? Joe?
Hello, thank you. I was wondering if you are also planning to do visual, to use visual cues, because in your samples, sometimes the person is not facing the audience, so you don't care about lip sync. So are you planning, in fact, to track head orientation so that to release, in fact, the constraints when the lips are not so visible?
Yes, we are planning to do that as a part of future work. And we are also planning to do, consider the morpheme tags that are there in Indian languages. So basically a phrase ends in a morpheme tag in an Indian language. So we can basically consider that fact as well in this lip sync video. And then we can, as you said, we can process the visual cues as well to get a better lip sync video. Yeah, these all goes in a part of in the future work. Yeah.
Thank you.
Thank you.
We have room 2 minutes for one last question. If no one, let me thank you again, Manu, for your presentation. Super interesting. And let's wait. I'll just wait 2 minutes just for, thinking, again, thinking with the next presenter. That will be presentation from, so it's a paper from Marko Nikolic and Vyacheslav Klimkov. I guess it's Slava presenting on site.
No, it's good.
Yeah, it's working now.
Thank you.
Okay, shall we start, Thomas?
Yes, let's go ahead. Thanks, Slava.
Okay, hi all. My name is Slava. I'm applied scientist in Amazon, and I would be presenting on behalf of Marko Nikolic and myself. The work is on homograph disambiguation. So basically, with the rapid development of neural text-to-speech, a lot of publications are on the back end, and the front end does not get that much attention. And the paper presents very, very simple technique, but just tries to close this gap, let's say, that when the natural language processing advanced very rapidly, we did not utilize this progress in text-to-speech front-end. So first, the problem formulation. So if you haven't faced this problem in your TTS experience so far, so homograph in text-to-speech, or more precise, heterophone homograph, means the word that is spelled the same, but can be read in different ways. So example would be much simpler to understand, perhaps. I have read a book yesterday. So in this case, word read has realization read, and we understand it perfectly just from the context. So there are different kinds of homographs. Most prominent ones perhaps are morphosyntactic and lexical. Morphosyntactic is when the different realization comes from the fact that the word has either different part of speech or different tense, like in the example. Lexical are more challenging, and this is just because the words are written the same but means different things. For example, bass and bass, fish and musical instrument. So the problem of homograph disambiguation is prominent in text-to-speech because we are meant to synthesize proper pronunciation given just the text. And when the system makes a mistake, it's very disturbing to the user. It shows the system as unintelligent and that it does not understand the message. So even though it doesn't happen often, it may be very disruptive. Moreover, in different languages, the amount of homographs varies greatly. And in Japanese, this is exceptional problem because there are, as we've seen before today, there are a lot of homographs. In my native Russian, there are a lot of lexical homographs, and it may completely change the message which you generate. So it's really important to do it properly. So the way how this publication appeared, one day I just stumbled upon this data set from Google, which contains the, let's say, English homograph parsed from the Wikipedia. It accompanies the publication from 2015, which presents the production homograph disambiguation in Google frontend. So the data set contains roughly 150 words. For each word, there is around 100 sentences. And for each homograph realization, it is annotated which realization is that. So in the paper, they bring up the numbers. So rule-based homograph disambiguation scores 88% accuracy. Simple machine learning based on some word-level features scores 95, and fusing brings 99. So 99 is already pretty impressive, and hardly you can shoot a lot better than that. But the fact that you need rule-based approach is a bit disturbing. So you can imagine that composing the rules to disambiguate homographs is very time consuming, and that's why it usually lands somewhere in the backlog and no one really tackles it. So it requires some linguistic knowledge. You may need to perform some software development, and sometimes you can cluster homographs and solve some set of homographs, but sometimes you have to do it per case. So that's why hardly it gets a lot of attention, even though everyone recognizes that this is a problem. So yeah, the paper was in 2015. So what happened since 2015? Widely, the contextualized word embedding starts to be used. And this feels like a perfect match for this kind of problem. So the most common, let's say, approach to generate contextualized word embeddings is to pre-train the transformer encoder on the large unannotated text corpora in order to predict some masked words, and then use the, let's say, activations as the representation of the word in the context. So in this particular case, yeah, you just get the set of the embeddings for the sentence, and you assume that the embedding for the word, for the homograph, contains the information which realization should be used here. So as a first try, we go for a very simple approach where we just train on top. We use the transformer encoder as the feature extractor, and we use a simple logistic regression on top per homograph, trying to classify which realization of homograph should be used in this particular sentence. So usual approach in NLP is fine-tuning the contextualized word embedding extractor, but we didn't go for it in this particular case. I would come back to it in a second. So overall, using the contextualized word embeddings for such a simple task might feel like an overkill because it's very computationally heavy to have the word embeddings extraction in the front end. But on the other hand, there are a lot of other tasks in text-to-speech which can benefit from having the contextualized word embeddings. For instance, you can use it for in phrasing model, or you can use it for prosody prediction. So that's why probably you don't want to fine-tune the word embeddings extractor. You want to use it as is, so you can reuse those word embeddings for other tasks too. Okay, so as for results, we did try quite a few versions of word embeddings extraction. So mainly BERT and ALBERT. And here is the results. So we score with this dummy approach better than the previously reported accuracy, which was quite surprising to get just from the first shot. And I think it just, yeah, the problem didn't get enough attention for someone else not to have a look how much you would score using such a simple technique. So we also got a bit curious. So what exactly happens when the disambiguation fails? So, and we looked into words where the accuracy was not 100%. So this is a subset of those. And when I was looking at this table, I immediately noticed some specifics. Mainly, quite often there is a disbalance in the training set. So second column shows the split of the training data, so for different realizations. So yeah, for the generic machine learning, this balance might be pretty hurtful. So we thought maybe if we would augment the data a little bit, we can fix those disambiguators for those specific words. So in the new split, this is the amount of data which for particular word which we obtained after collecting a little bit more for this particular case. So we collected the additional data for the most disbalanced cases, and almost in all cases we did fix the incorrect classification. So we recovered from 87% accuracy to 97%. So a little bit more on the model. So as said, this is just a simple logistic regression. So in terms of parameters, that's just an affine transform, which converts your word embedding, so whichever dimension you have. For BERT, it's 768 to the number of realizations of the homograph. So usually it's 2, like read present, read past. I think in the data set, it was maybe 2 or 3 cases where there were more than 2 realizations. So in 16-bit precision, it takes 3 kilobytes per word. So if you think how many homographs you have, let's say 150 or 500, probably still not that much of a memory, but we had a quick look whether we can reduce the memory consumed. So we applied a gradual sparsification during the training. That means they refine the connections gradually and leaving just 10% of the initial amount. So that results in the model size of 300 bytes only, and it did not affect the accuracy. So that means that, even though that we have a very high dimensional input, we may not overfit and still perform more or less generic disambiguation. So regarding the data collection and coming back to my initial mentioning that it's difficult to create the rules for homograph disambiguation. So in case if you use such an approach, it becomes much simpler. So for example, you can have a huge text corpora. You just request all the sentences with the word that interests you, for example, read. You select randomly 100, 200 sentences. You pass it to manual annotation, which does not require any linguistic knowledge. It just can be done by any native speaker. They annotate which version of the realization is used in particular sentence. You train your per homograph disambiguator and consider it done for this particular word. So most of the steps, apart from manual annotation, can be automated. And to annotate like 100 sentences, it would take maybe 1 hour of one person to do. Even more than that, you can automate the whole process if you have a large text and audio corpora, something like LibreSpeech. You can select text and audio and pass them to the forced alignment, which would define which realization of homograph is used in particular sentence, and you can use it in training. The only drawback is, of course, that you may need the automatic speech recognition with stress, because some of the homographs differ in terms of stress, for example, impact versus impact. So yeah, that's roughly it. As a conclusion, it looks like the contextualized word embeddings contain the required information to disambiguate the homographs. You don't need to fine tune anything. You just need to train a simple affine transform on top of the word embeddings. So the model can be as small as 300 bytes per word. The data collection becomes much cheaper because you don't need any experts to compose the rules, or you just need native speakers who would be able to annotate which version of the homograph used in particular sentence. It works to keep your classes balanced, because it looks like if you would just sample randomly from the sentences with particular word, for some words you may end up in situation that a particular realization of homograph is underrepresented. And finally, if you're already using contextualized word embeddings for other tasks in your text-to-speech system, there is no reason not to use them for homograph disambiguation as well. Okay, that's it from me.
Thanks a lot, Slava. Thanks. Right. Thanks a lot. We will go to the questions. In the meantime, I have a question not to you, but I see some Japanese speakers in the attendees. I would be curious to know, or maybe you know it, Slava, right? What is the accuracy in Japanese, Korean, Chinese, or other Asian languages for homograph disambiguation? It's pretty high, right? In English 99, but is it the case also in Asian languages? Do you know? Slava, do you know by chance? If not, I would be curious if Japanese speakers here would have any idea.
Yeah, so I think that the the rate where the complete sentence in Japanese is correct is rather low. It's like 80% maybe. So that means that every fifth sentence may have some disambiguation problem.
Right. All right, let's move to, thanks. It's not Marco, it's Slava. Any comparison in performance with the rules or rules plus machine learning pipeline? And by performance, do you mean accuracy here, or do you mean computational performance, Jason? Computation.
Okay, so as for computation, I guess if you take into account the extraction of the contextualized word embeddings is pretty expensive, as I said, a bit of an overkill. But if you extract the contextualized word embeddings for other tasks, I think is basically free because you just need to perform this single layer affine transformation.
Right, but do you get a sense of what it would be for the, because you started presenting the baseline for purely a rule-based approach and then ML plus rule-based. Do you know how it compares? Do you have, from the top of your head, any gross estimates?
No, I don't think so, because right. Yeah, those rules are generally not computationally heavy. It's rather whether word water is met some few words before. So it may be big in code, but doesn't take any time really.
Right, in terms of latency. Thanks, Jason. Are there more questions on sites or in the chat? Don't hesitate. Gérard?
Yeah, so you should work together. In fact, there is a big difference between field FIS, so an accident where you have two homographs, they're very unusual, like bass and bass. But you have more regular ambiguities, like this verb noun in English, where you have this position. It's systematic. Every word in English has a verb, like in French, supporter, supporter, this kind of stuff. So how you can somehow classify between what can be solved by rule and one could be solved just by irregular word.
Yeah, exactly because of that, the classical approach, I would say, would be just use a part of speech tagger or morphosyntactic features. And this, for English, it solves overwhelming amount of issues if you do it correctly. But as I said, it differs between languages, like whether majority of homographs are morphosyntactic or lexical based. So in some languages, you have a lot of lexical ones. And I would say they are more hurtful if you do it wrong because it changes the meaning of the message. So in perception, I guess it's important to do them right too. So yeah, that's why overall the accuracy percent is so high for this rule-based, because perhaps most of the issues are solved simply by defining tense or part of speech. But this is for English. For others needs attention to, and they are the most problematic. But fortunately for this approach, it does not matter. So you just solve both in the same way, and you may not even know what exactly is the underlying difference between the two.
Right. More question? Anyone on site?
Yeah, I was just curious if you tried different layers of the model or if it was always the last layer that was best.
Yeah, so honestly, we did not experiment that much in terms of the model or the exact features that we used, because on the first shot, it gave very high accuracy. So I quickly checked whether, for example, not one layer, but 2 layers would give slightly bigger accuracy. It wasn't the case, so I didn't explore it any further. I think it's more important, like whether your data is collected properly, and then you train this simple model and it would be sufficient, because the those contextualized word embeddings are so powerful that you know, you almost get this disambiguation for free. It doesn't really matter like what you do on top.
My question will be actually about the sample sentence, because if I understood it correctly, at least if I remember my English teacher well, then the test sentence, I have read a book yesterday, is grammatically not correct, because that's past tense. So it should be, I read a book yesterday, or I have read a book during the last time or last years or whatever. So my question is, how can you detect if this is just like a mispronunciation or some grammatically wrong sentence, and then that exclude it, or what to do with it if you just synthesize something by random, or well, what is the solution? Because now, like, I speak English, so, and of course I make a lot of errors. And actually, nobody knows what is the correct English anymore, because there are so many dialects and versions. I was told, for example, that most probably the members of Beatles would fail most regular language exams, even already at that time, and the situation is getting worse since then.
Okay, so maybe I would bring up an example which Marco showed me, which we found curious to discuss, and maybe that would answer. So we were curious how it would disambiguate the sentence such as "I read a book," which does not explain whether it's a past or present. So it could be both, because you don't have enough information about it. And it picked the past with slightly lower confidence. And we asked just people how they would do it. And it occurred that native speakers would pick the past tense. So apparently it's just whatever you have more in the text corpora for the contextual word embeddings training that would define your classification. But interestingly, the probabilities which are outputted by logistic regression were sort of meaningful. So in this particular case where you have the ambiguity, the probability wasn't like 0.95, which was usually the case. It was rather 0.6. So maybe you can build your logic on top of that.
Right. Thanks a lot, Slava. Time to move to the next speaker. Thanks a lot. And last talk is from Jason from University of Edinburgh. It will be about polyglot synthesis. Jason?
Hello, guys. Thank you for sticking around to the last talk. It has been a long few days, especially last Saturday. Let me just share my desktop.
I can see.
You can see it, great. Can I just check if the audio works?
Sure thing.
Putting green light or in mix?
It does, yes.
Okay, great. So today I'll be presenting some work on kind of analyzing whether you can take sequences of VQ-VAE tokens and rearrange them at word boundaries. And then when you resynthesize these rearranged token sequences, is intelligibility affected by this kind of rearrangement? And this work is done in collaboration with Jennifer and Simon. So my main motivation for this line of work is really to make low resource TTS systems more viable. And so in my imagined low resource scenario, a language might not have any linguistic resources, including phonetic resources. So they would be grapheme input only. So yeah, we train using only graphemes in this scenario. And so, one important thing is pronunciation control, but to do this via graphemes is quite unpredictable. And I don't think this is done very often. So one way you might want to, a possible way of controlling pronunciation via graphemes is to use newspaper misspellings. So for example, if you have the word furlough, and if this was input into an end-to-end tachytron system and it's pronounced as furlough, because of words like borough, then you might want to respell furlough, the last part of furlough, in the following way. And in many cases it might be pronounced correctly, but you don't have any guarantee of whether it will be pronounced correctly. So what's a potential solution to this issue? So one solution is maybe we don't have to use graphemes to respell and correct pronunciations. Another option is instead we can correct mispronunciations through audio exemplars. So in this example, instead of respelling the word at the grapheme level, we would have an annotator record the correct pronunciation, get some kind of semi-supervised speech representations from that, and then feed that into the model. And hopefully the model would more reliably correct the pronunciation, because these speech representations are acoustically encoded. And so we have more control as an advantage. Another advantage is that annotators would require very little training. And another advantage is that you might be able to crowdsource pronunciation variations in a very simple and easy way. Maybe, from online videos or something like that. So we want to change the pronunciation of a single word, but how do we do this in utterance? So although I haven't built a full system for this so far, one strategy could be we kind of just replace the graphemes with these semi-supervised representations. So the TTS model would receive graphemes, some VQ-VAE tokens, and then graphemes again. And this kind of setup could work because we've seen some work in comparing the use of using both graphemes and phonemes in input during training and inference. And that was in a paper called Representation Mixing. And during training, in this model with VQ-VAE tokens, words would be swapped to their tokens if we had them during training with some kind of probability. And in that scenario, the model would be able to, interchangeably either use graphemes or VQ-VAE tokens, potentially. So in another strategy, maybe instead of having grapheme input to the system, we just have VQ-VAE token input to a system. And in order to do that, we would need to convert every single grapheme word to its VQ token sequence through some kind of lexicon lookup. And then in order to make a correction, we just make a recording for the single word which was mispronounced. But is this actually possible to kind of, take an isolated word and plop it into another sentence? Because, these VQ tokens are quite temporally sensitive. And it's hard to really know how sensitive they are. And so in this work, we examined this question Yeah, so these tokens are also bound to be contextually dependent in terms of time, because they are decoded in a very temporal way by like a wave RNN, for example. And so the goal of this work is to really evaluate the adequacy of using VQ-VAE tokens to correct pronunciation, either at the word level or like a sub-word level. And we do this by, changing their position in time. So more concretely, we don't rearrange at the word level, but we rearrange using a word boundary two utterances. So for example, if we take this utterance and take the second half of it, and then if we concatenate it to the VQ-VAE tokens for the first half of another sentence, then we get this combined sentence. And then we take this VQ-VAE token sequence and use that to condition a wave RNN. And then the question is, are the words at the boundary affected by this kind of mismatch in contextual features at the boundary? And in this study, we just look at the word after the boundary and look at how its intelligibility is affected. And so I'll describe our experiments. And our model is a very popular GitHub model, which is basically a speaker conditioned VQ-VAE autoencoder, where the decoder is a wave RNN, and it's trained using the usual reconstruction loss and codebook loss. And the data we use is all data of VCTK and all 109 speakers. And then we use, we get word level alignments from Montreal Forced Aligner. And so I will describe the methodology for like rearranging subsequences or like sequences of words and their token sequences. So first we extract token sequences corresponding to 3-word long chunks. And then we concatenate these 2 chunks together so that we get like 6-word long token sequences. And then we use those to condition a wave RNN and resynthesize to get speech. And then in the evaluation task, the goal, yet again, is for the evaluator to transcribe this 4th word here, which occurs after the concatenation boundary. And so to design the stimuli sets, we first asked, what kind of questions do you want to answer? So the first question is, first of all, just can we use these to control word level pronunciation, or are they just completely infeasible? And then the second, probably more interesting questions are, if linguistic context changes across the boundary, how does it affect the intelligibility greatly of word 4? And also the speaker identity changes also affect intelligibility. And so with these questions, we created 5 test sets. So test set A is kind of our baseline copy synthesis. B and C is mismatching the speaker. Sorry, B versus C, and then D versus E is like mismatching the speaker. And then B and C versus D and E are mismatched linguistic contexts. And I'll go into what do I mean exactly by mismatched linguistic contexts in a second. Yeah, so basically we generate using different speakers. So here E is generated, the first half of the sentence is from one speaker, and the second half of the sentence is from a different speaker, because we have mismatched speakers. Also the context of word 4 and word 3 here are also different. And then A for copy synthesis, the speakers are the same. And also these words are taken from the same utterance. So there's no kind of splicing and then concatenation going on. So each test set has 40 stimuli. So there's 200 stimuli in total. There are 40 unique first half sequences, which are shared across each test set. And then each of them are followed by 5 unique 3-word sequences. So what do we mean exactly by matching or mismatching linguistic contexts? So in this work, we simply just say, okay, we want to check whether the rightmost triphone of word 3 mismatches or matches the leftmost triphone. So here, because they share, these two phones here share with these two phones here, we consider that matching. And that's because of the word following will and then snow preceding world. And then in this example, we have mismatching contexts. And because I've changed snow world into Svargo world, you can see how this left triphone context mismatches now with this, with the valve here. So how do we choose the speakers for evaluation? Obviously, you couldn't choose all the different speakers because I wanted to make comparison between the speakers and still have a decent number of stimuli. Yeah, we wanted to investigate whether like certain speakers would be like less intelligible when performing concatenation. We found that like using slower speakers provided more reliable reconstructions. Faster speakers would kind of get garbled a lot more frequently. So we chose 4 of the most slowest male voice talents, and we generated 50 stimuli for each of them. And so here you can see how those stimuli are shared between the stimuli sets and also the speakers. And then for the mismatching speakers, where here are the speaker combinations. And when we generate those stimuli, all 6 words are conditioned on the first speaker ID, even though the last 3 words are obtained by encoding the second speaker ID, speech from the second speaker ID. So for our intelligibility test, again, it's fill in the blank task, 50 participants, and the stimuli were randomized on a per participant basis. All participants see all 200 stimuli. And then we manually corrected any errors that they might make. So it's misspelling such as contenders versus contendors, typos such as fresh and frush, and homophone ambiguity errors such as road, road, and road. I'm not sure if this is pronounced differently in American English, but yeah. Results. Okay, so here's just stimuli which had a pretty high accuracy. So here's the first one.
Putting green light or mixed.
So that's copy synthesis, no issues because both the left and the right, so you see this plus sign indicates the concatenation boundary. Both the left and the right subsequences come from the same recording.
Putting Greenland love with Scotland.
So here we can see that because they're now concatenated, there's been an N sound kind of inserted before love, potentially because of some kind of alignment issue.
Putting Greenland and any further.
Similarly, we get this on C.
Putting Greenland's call Stella.
So it seems like was introduced between green and call.
Putting Greenland's a bring these things.
So bring is quite intelligible, but then there's like something else being inserted before that. In this study, we don't actually penalize the model for doing any insertions, but that could be left for future work. So yeah, maybe these errors are possibly due to the contextuality of these speech representations, or maybe some alignment error of our ASR aligner. Here's like 2 frequently mistranscribed stimuli. So here's the ways that call was mistranscribed. It was mistranscribed into little, basically.
And the sun made strike a little Stella.
And it does really sound like little, not sure why. And then here, things was mistranscribed into, it seems like the leading consonant was mistranscribed.
The rainbow depends considerably on things with it.
And yeah, it seems as you listen to it, the consonant is just garbled really. So here are the listener test results. So we have, each of those 5 test sets. And the first takeaway is that, copy synthesis is the most intelligible. And that's probably just because there's no possibility for alignment errors or any token contextual mismatch. The second takeaway is that BNC, for BNC, the linguistic context matches across the concatenation boundary, whereas for D&E, the linguistic context mismatch. And so there's a distinct difference here, which is kind of promising for like this as a paradigm for like pronunciation correction. And what's also promising is that like when speaker is different across the concatenation boundary, there's no real hit to intelligibility. And I guess this is like a testament to these like VQVA models' ability to disentangle or to not include speaker information in the code book space. Also, to analyze these results further, we looked at like speaker combination results, and we found that for the orange bar here, orange bar results are where speaker ID changes across the boundary, and the green bar results are when it's always the same speaker across the boundary. And you can see that the orange bar is always lower than the teal bar. Also this depends on the speaker as well. So some speakers are not as good as like, you know, being concatenated with other speakers. So it depends on the speaker or speaker combinations. We looked at some of the speaking rates, and we couldn't really see it being due to like phone durations or silence durations. So maybe this requires further analysis, but maybe it's like due to like per speaker habits or accent differences. Also, certain speakers are just less intelligible in general. Maybe one potential explanation is that this speaker had very little silence in its recordings, and maybe this made it harder for like the VQV encoder or the forced aligner to identify boundaries, interword boundaries. Not sure about that. And then we had some surprising qualitative findings where, sorry, am I running over time?
Yep, yes.
Okay. Okay, nearly done. So basically we found that sometimes the leading consonant was correct, but then the following word was incorrect. So here's one example.
The long-term sequence is negative.
And here's another example for come.
At its annual colmat.
Where we actually expected the other way around, where the consonant would be mistranscribed and the rest of the word would be correct. So conclusions. I think this kind of unit selection like speech generation is possible, perhaps. And these VQ tokens are temporally, linguistically context dependent, but not speaker contextually dependent. And this is quite promising if we want to use these speech representations to measure aspects of speech, such as pronunciation in like a very low resource setting. And for further work, I want to try and discover less linguistically and temporally context-sensitive speech representations, and also examine if these representations can be used to control like subword pronunciations. Also transferring to like low resource languages, and also want to remove the reliance on like pre-trained ASR aligners. Yep. Thanks for listening.
Thanks, Jason. And of course, that was not about polyglot. I got confused with your paper from yesterday.
Oh, yeah.
All right, we moved to questions. In the meantime, so you explained the robustness to speaker mismatch by the disentanglement capabilities, right, of the VQV?
Yeah, is it this graph, right?
Exactly, yes.
Yeah, I mean, upon listening to the stimuli, there's no audible change really in speaker identity to my ears.
So how do you interpret that, right? That's my question, basically.
Well, I interpret it mostly as because the way that the VQVA is, the model is trained, the speaker embedding is conditioning the wave RNN, so that I don't think the VQVA encoder has any pressure on it to capture speaker information to improve the reconstruction loss. Yeah.
Okay.
So it can kind of safely ignore it. Yeah.
Mm-hmm. Right. We have time for one or two more questions. in the chat, anyone on site? There are no questions in the chat? People in Budapest?
Yeah, it's late in the day, I guess.
No, so, right, I see one question from Sebastian. I have likely misunderstood something, but why would you change the speakers exactly as such boundaries?
That's a good question, Sebastian. I think the first reason is just curiosity, because there aren't that many other ways we can change. Given that we're using VCTK, there's not many other ways we could actually change something across the boundary. But I think in terms of application wise, if we are designing a system where we can correct pronunciations, ideally we don't want to get the original speaker in to correct the pronunciations. So ideally anyone can provide corrected pronunciations.
More questions?
Thanks.
Right, so let me thank you again, Jason, for the presentation. And yeah, wrapping up, it was the last last presentation of the last session. I'll hand it over to people in, I guess, Geza, right, for the closing ceremony.